Hey, Jim, thanks for joining us today. First of all, how are you doing and where are you talking to us from today?
Hello, Jamie. We're doing very well. We're ensconced in our home in Minden, Nevada. It's been smoky, but today is nice, clear skies.
When the year started, I'm sure this isn't where you expected to be come September timeframe. What was the original plan for 2020? And tell us a little bit about why the program got derailed.
Now, the original plan as of January was to take the Perlan 2 back to El Calafate, Argentina, and attempt some more high altitude flights and do some high altitude research. But of course, when the COVID occurred and caused travel restrictions, it made it impossible for us to ship the Perlan 2 to Argentina and of course do travel to Argentina. So we are here in Minden, Nevada, and for me, it's been an interesting summer. I got involved in a project that built a new sailplane, which has fly-by-wire control system on the wings for the flaps and ailerons. I've flown it about 140 hours this summer, claimed 5 records, and as part of the Minden Soaring Club, we won the World Championship in the OLC Online League. So we've had fun. This airplane's been fun to fly. It's got a 92-foot wingspan, which is 8 more feet than the Perlan. It's got a bigger wingspan, but a smaller wing, which is optimized for high-speed cross-country flights at lower altitudes.
And you're talking about the Nixus program, correct?
That's correct, yes.
So explain a little bit about the benefits of the fly-by-wire system for something like a sailplane. I think, typically we think fly-by-wire, we think of something like an Airbus A320 or a high-performance combat aircraft where the aerodynamic loads are strong or the aircraft is inherently unstable. Why do you need fly-by-wire in a sailplane, and how does it compare to flying Perlan, which of course doesn't have the fly-by-wire system?
The fly-by-wire is only in the wings. For high-speed flight, you need to adjust the trailing edge of the wing in order to keep the laminar flow on the wing. And the fly-by-wire system is set up to do that. Some reasons for using fly-by-wire versus mechanical system. On a very long, thin wing, it's very difficult to put the mechanical hardware required to move the control surfaces into that small area. When you have fly-by-wire, you can optimize more readily. In the case of the Nixus, we're using automatic flaps. So the aircraft is calculating the angle of attack and the lift coefficient and adjusting the flaps based on that so that it is optimized.
The Nixus aircraft that you're talking about with the fly-by-wire system is a sailplane just like Perlan. What are the differences in terms of the aerodynamic forces that you feel in a fly-by-wire versus conventional sailplane? And is fly-by-wire anything that could potentially be integrated into Perlan in the future?
The fly-by-wire system, the thing that you notice most as a pilot is that the aileron roll forces are much lighter. The Perlan has relatively high aileron forces, so if you integrated this system into the Perlan, it would make it easier to fly it.
From a piloting perspective, how different does the aircraft feel as you're ascending up and the air is getting thinner and thinner and thinner in Perlan?
As you climb with the Perlan, we're still flying the same indicated airspeed. As you get to higher altitudes, it rolls a little bit better because you have less roll damping. But in general, the stick forces and stick deflections are very similar at high altitude as they are at low altitude. So to the pilot, there's not a significant change in the flying qualities of the airplane. The biggest change is that your true airspeed goes up. As the airplane flies, it needs a certain amount of energy in the air to create lift. And we have a little pitot on the front of the airplane that measures the impact of the air coming in the front. As the air gets thinner, the airplane actually has to go faster to have the same impact pressure in the nose. The impact pressure is our dynamic pressure, and that is the pressure that's required in order to generate lift. It's very interesting. As the air gets extremely thin, the airplane's going much, much faster in what we call true airspeed for the same indicated airspeed. At 90,000 feet, it's 6.7 times the indicated. So the airplane's actually going pretty fast at high altitude. The only thing you notice as a pilot is that the turn radius gets larger as you go faster for the same bank angle. And at altitude, it can be much larger. But in terms of flying the Perlan to high altitude, typically we have a very strong wind from the west as we're getting to high altitude. So the true airspeed really is a good factor. And we just zigzag back and forth over a line on the ground where this rising air is.
Explain a little bit about how you can be going so fast in an aircraft that doesn't have an engine.
Well, it's a matter of the rising air currents. When we're flying in the mountain wave, the air that we're flying in is rising faster than the airplane is sinking. As we go up in altitude and the true airspeed goes up, the sink rate of the airplane also goes up. But as long as the air is rising faster than we're sinking, the airplane's going to climb. We have discovered that in the polar vortex region, the mountain wave can be extremely strong at high altitude.
So you're essentially flying the aircraft downhill. You're basically trading your altitude to get that airspeed that you need, but you're doing it in an air mass that's moving up faster than you're moving down.
Exactly true. Yeah, glider is always sinking through the local air mass, but if the local air mass is rising either from a mountain wave or a thermal, the glider actually can climb and go to higher altitudes.
In 2018, September 2nd, you flew to 76,124 feet with Tim Gardner in the back seat. And that doesn't sound that far off from the service ceiling of the aircraft, 90,000 feet. But from an aerodynamic standpoint, it's actually a fairly significant difference, isn't it?
Yes, going from 76,000 to 90,000, there's even thinner. And the true airspeed goes from about 4.5 times indicated airspeed to 6.7 times indicated airspeed. So as you go higher, the turn radius is going to go up. The other thing that occurs as you go higher is you start to get closer and closer to the speed of sound because the true airspeed is going up. When you get to 90,000 feet, the stall speed is going to be 39 to 40 knots. Our limit speed is 54 knots indicated airspeed, which is over 300 knots true airspeed. And the limit, high speed limit occurs because at that altitude, the Mach is high enough that we're going to start getting shock waves on the wing if we go faster than 54 knots indicated airspeed.
Just to break that down into sort of layman's terms, when you talk about the true airspeed of the aircraft, what does that really mean?
If the air mass were still and you were on the ground observing the airplane, that would be the speed that you would see the airplane moving. So if I'm at 90,000 feet and I'm at 50 knots indicated, my actual true airspeed would be 6.7 times that. So that's almost, what, 350 knots. So if the air was still and you were on the ground, you'd observe the airplane moving at 350 knots, even though the indicator in the cockpit is only saying that I'm going at 50 knots.
And that's because at that altitude, the air density is such that from the wings perspective, I guess, it's getting the same amount of air molecules as you'd get at sea level at that, 40 knot or whatever airspeed.
Exactly. Good way of describing the term is the number of air molecules that are going over the wing. They have to be constant.
What are the objectives for the 21 flying season that carry over from what was originally planned for 2020?
Well, the biggest objective for the year is to add some science payloads and take Perlan back to Argentina and attempt to fly higher than 76,000 feet. We have a new GPS radio occultation sensor, which is going into the tail tip. It is unique in that it measures the signals coming from GPS satellites as they move above the horizon and as they set. And what this allows engineers and scientists to do is determine the amount of humidity that's in the atmosphere by looking at the changes in the radio signals versus a nominal signal. They can determine that their mass has a certain level of humidity. And from that, they can enter the data into computer models for weather forecasts and potentially make weather forecasts better.
setting aside all of the piloting elements of this, what does it feel like to be at 76,000 feet? What will it feel like to be higher than that, even when you look out the window next year?
Wow. Well, for me, it was a dream of a lifetime. So there was a huge sense of satisfaction in being able to accomplish what we'd set out to do. In terms of the environment inside the cabin, the cabin is no different. Looking out the window, it's an amazing vista, though. You can look at pictures from high altitude, but to actually be there is really phenomenal. Of course, it's pretty cold outside, and the Perlan doesn't have a heated cabin, so it's a little bit chilly inside. But the amazing vista, the sky is dark, as you see in the photographs, and you can start to see the curvature of the Earth, and it's one of those things that just says that we're actually kind of small creatures when it comes to the big picture.
Well, Jim, any final thoughts that you'd like to share with your followers?
I'd just like to say thank you to all the people that have supported the Perlan project over the years. It's been an ongoing thing. We've had many people donate, from Airbus to Dennis Tito and other groups, and we wouldn't be here without their support. It has been a fantastic journey. We've learned a lot about pressurizing a sailplane without having an engine to provide the air source. And it's been tremendously satisfying to be able to put all this together and to accomplish the science and the flying that we've done.
Jim Payne, Chief Pilot of Airbus Perlan Mission 2, thanks so much once again for sharing your time and your knowledge with us. And I hope the next time we get to talk to each other, it's in person down in Patagonia.
Amen, Jamie. Thank you very much. It's been a pleasure.